So, hello everyone. Welcome to today's Women in Network Science seminar. Today we have a Pathways in Network Science talk with Roberta Sinatra, whose research focuses on quantitative understanding of social systems based on massive data sets. She's a physicist by training, but also well-read in the social science literature, develops and applies methods from physics and complex systems, machine learning, and statistical analysis to social systems. She's well renowned in the scientific community for studies about complex social systems and theory and applications in network science. She's pioneered breakthrough publications in top-tier journals like Nature Science, PNAS, Nature Physics, and she's received extensive attention from the scientific community for that, and is also routinely invited to give excellent talks as she is today here. We're very excited to have Roberta here today. So please, Roberta, take the stage. Thank you for being here.
Thank you, and thank you for the invitation. So let me share the screen. So my slides, just give me, yes. And here it is.
Excellent.
Yeah, I just wanted to say, yeah, it's really my pleasure to be part of this series of events. I remember when they were created, I think it's 2 years or 1.5 years, something like that, right? Is that right?
Yeah, we started in 2020 when everybody was at home.
But perfect. And I thought, oh, what a great initiative. So I'm particularly happy to be here. And yes, so I think the talk that I prepared has two components. One is, okay, pathways in network science, basically my career trajectory within network science, but also starting from network science. And then I have a component more research-based, so about the results of research results about biases in scientific success. That is really important topic in my research agenda. But having said that, I have prepared slides, but I'm happy to just put them aside and have a nice discussion with basically primarily questions and answers about any aspects of this, or I can go the standard way and talk. So I don't know, Alice, how we want to do this. Perhaps
perhaps we can get started on your presentation, and if people want to jump in, you can post in the chat. I will monitor that. If there's like stuff coming up in the chat, Roberta, I'll just interrupt you, and then we can take it from there.
Great. So just reiterating, I'm fine with keeping this informal since it's a small group, and also the purpose of this is to network, right?
Yeah.
And to create a community and sharing also successes, challenges, and so on and so on. This is best done without a monologue, but more with a conversation. Okay.
Agreed.
I'm gonna go with this. So I think so. If I had to summarize my career, my research career in one word, this word would be really interdisciplinarity. Interdisciplinarity and in all its aspects. And this journey, this interdisciplinary journey, started in a place called Scuola Superiore di Catania. This place is located in Southern Europe, in Southern Italy, on an island, Sicily. And when I talk about to a community of network scientists, everybody knows the importance of first mover advantage, or the initial advantage that you can get when something starts. This was my first mover advantage. This is where everything started in my career. Scuola Superiore di Catania was a special place where I met incredible researchers and incredible also network scientists, and I really think that gave me a boost that still has effects today on the way I do things and the way what I've become today. So everything started here in Sicily, and then so I started Scuola Superiore di Catania, which is an institution that offers free bachelor and master education. And at the same time, you can, a student can start research projects with the faculties that work within the Scuola Superiore di Catania. So you study and do research at the same time, and everything is for free, which is not granted in a country like Italy. And from the University of Catania, where I also did my PhD, I moved to Northeastern University for my postdoc. Northeastern University hosts the Network Science Institute, which has for sure very well known researchers in network science. Now I don't want to forget any, but like people like Alex Vespignani, Laszlo Barabashi, David Lazar, and many more are there. So it was really the Mecca for me. It represented the Mecca of network science, and this is where I grew. I learned a lot, and I spent 4 very formative years of my career. Good and bad years, but definitely formative, important for what I am today. And after that, I moved to CEU, to Central European University in Budapest, for tenure track position, also in network science. And I spent 3 years in Budapest. Before my tenure track was completed, we decided, my partner, my husband is also an academic, we decided to move to Denmark, to the IT University of Copenhagen. At the IT University of Copenhagen, we co-founded a group called Networks, Data and Society, or NERDS research group, and all my creativity in names was exhausted by creating the NERDS group. I think it's the best written output that I could produce. And I'm particularly proud of this group because, well, there are wonderful people in it. It sparks really a lot of good things, a lot of good projects, and Sim won the prize for research environment, for the best research environment in Denmark. And definitely having a healthy, nice research environment is something that I value a lot, that we all value a lot in the NERDS group. So I'm particularly proud that we made this and that the group won the prize. And now, right now, I'm at the University of Copenhagen. So I changed job actually 2 weeks ago, October 1st, 3 weeks ago. And while I still keep an affiliation with the IT University of Copenhagen. So this is, these are my the main place of employment, but my pathway in network science is also, during this pathway, I've also visited a few other places that have been very important, again, in shaping my research, in meeting great people, and they are on the screen, but I think that the most formative ones were for sure the Complexity Science Hub in Vienna, the Santa Fe Institute in the US, and the ISI in Turin, with which I still have formal affiliation.
And so, Roberta, we have already our first question in the chat.
Yes.
So Caitlin is interested. in hearing more about how to create a healthy research environment, because she's a new PI and is building her own research environment.
So again, I tend to be cautious on extrapolating rules from one data point. I can say how we do it on Nerds. I don't know if this is the only way or a successful way, but I'm happy to share this our thoughts. So first of all, one needs to want a healthy research environment, meaning one needs to be sensitive to the issue, right? Research and research environments can become easily toxic, because there is a lot of competition, because there is not really a control from above, especially for PIs, right? So PIs can become really small dictators if they want in their research group. So there is a lot of research that shows that a research environment can become easily toxic. So first, one needs to be to care about the issue. In practice, in our group in Nerds, we have a very, so because hierarchies can create toxicity, we try to have a system which is as flat as possible, where we take most of the decisions in a horizontal way. And this means that we have a group meeting where we discuss issues with master, PhD students, postdoc, assistant professor, up to the highest level. This doesn't mean that everybody can do everything, right? A PhD student still needs a mentor, still needs to be guided in decisions, but there are some decisions that do not need to be made only from the top, and talking about struggles, talking as a professor about struggles of a professor, talking as a PhD student, the struggle of a PhD student helps to feel part of a group, share the struggles, right? Share the successes and feel more comfortable. I think this is the most important ingredient. I'm sure that the members of the group would add more. Actually, I have to say that the application for nominating the group as best research environment doesn't come from the professors, from the PIs, but comes from the non-tenured staff. So specifically in our case, it was a PhD student and a postdoc that made the application, and they had their own reasons. So yeah, so I'm reporting some of this. Any follow-up question on this? And I'm sure that, thank you. I'm sure each of us has different or different opinions. So I think the important element is to incorporate or to discuss whenever there is an issue, right, coming up. And that helps to create a safe place and make the environment more welcoming. Yeah. Yeah, but I'm glad that people are interested about this. Oh, sorry, something has happened here. Yeah, great. So I was saying that, yeah, interdisciplinarity, I think, is a good term that summarizes my career. And I have been changing topics a lot during the years. So I started doing research in 2005 when I was at the end of my bachelor. And I basically continued until today, until 2022, with just one short gap, one maternity leave. And I have changed topics a lot. So I have a background as a physicist. My bachelor was in physics and my master was in theoretical physics. And early in 2005, my topics were really very physicsy. So I was working on statistical physics of networks, random walks on networks. There was a lot of what I was studying for my bachelor and my master in my research. And then as I moved to my postdoc and to the various places that I mentioned, my research became more and more social sciencey, but still in the realm of computational social science. So today I'm not sure what I am exactly. I'm definitely not a pure physicist. I'm not a social scientist. I'm not even sure I'm a computational social scientist in the way that many people think about it in a conference like IC2S2. I'm definitely familiar with many of these topics and research areas. In general, I don't like giving labels. I think it's important to do good research, sound research, whatever is the field that it fits in. Yeah, that doesn't matter too much. But my career trajectory moved through many topics, going from more physics topics to more computational social sciences topics. One thing that occupied a lot of my time was research on science of science. And actually, the research topic I prepared for today to talk about falls in this area, in the science of science. Together with science of science, what keeps me busy today, I mean, really in 2022, are also randomized control experiments in different areas of social science, but especially in social media, and in the way we perceive performance and success. More of this in a second. And also I work on algorithmic fairness and bias. Algorithmic is between brackets because we can talk about fairness and bias also in data without having algorithms. The algorithms is more the application domain. All right. Oops. And just wanted to say, so I started with this discussion about my trajectory, my pathway within network science, and starting from network science. I always, when I talk, especially with students, I say, this is just one data point. And I don't think this is the way to get, I don't know, a tenured position, or necessary tenured position. Like all the stories of survivors, it suffers from survivor bias, right? So I could say, yes, you should do a postdoc position in the US because this is great. This is what makes you get then a tenure track position in Europe and so forth and so on. I mean, this is all a flawed concept because, yes, survivors talk about the past, and we don't know what has happened to those that didn't land, for example, a tenure track position. I'm using here this analogy, survivor, non-survivor, because this is the term used in the literature. There are a lot of great careers, not in academia, that do not end with a tenure track position. So the term doesn't want to imply that there are tier A, tier B careers, but yeah, meaning by survive, I mean those that survive within academia, that decide to stay in academia. So nothing really to extrapolate from my trajectory. It's just a story, one story of a person that started in network science, had a lot of fun, and managed to arrive at this point. Okay. Are there any questions about this? Happy to share any detail. Okay, so then perhaps we can talk more strictly about research. So what is that one project that I've been working on. And the project is about bias in science, and how we measure bias in science. But before doing that, I need to take a short detour into the world of art. And this is to illustrate the premise of my research, the premise of the research I start from. And I want all of you to think about the first piece of art that pops into your mind, the most famous piece of art that you can think of. Now, if I'm in a room, I ask people to shout the name. If you're fast enough, you can type it on the chat or just unmute yourself. But in most cases, yes, exactly. And this experiment never fails me, right? So most people think of the Mona Lisa, and this is indeed the most famous piece of art in the world, even the most parodied piece of art in the world. If you have been at the Louvre, you know what I'm talking about, right? You have experienced it, all elbowing to take a glimpse of this painting. But what many people don't know is that the Mona Lisa was not always so famous. It became famous at the beginning of last century. After it was stolen. So the painting was stolen. It took 3 days to realize that the painting had disappeared. And after that, people started talking about this painting. It must have been a wonder of exceptional quality to be stolen and to receive so much attention. And then when it was returned to the Louvre, well, this phenomenon that you see in the photos started emerging, right? Crowds gathered at the Louvre to see the painting. So the story of the Mona Lisa shows the difference between two concepts, between performance and success. So performance is an instance, the Mona Lisa is an instance of Leonardo da Vinci's performance. Success instead corresponds to what people think of Leonardo's performance, so how they perceive the Mona Lisa. So in other words, performance is about you. It's an individual attribute. It's your paper, it's your piece of art, it's your work. While success is about us, is a collective phenomenon. It reflects our perception, so captures how we perceive performance. And why is this important? Well, it's important because today we have an obsession with success. What we do is trying to measure success all the time, and we use measures of success as a proxy of quality, as a proxy of performance. And we do this because it's easy to collect digital fingerprints that humans leave. So it's easy to quantify success, while it's very hard to measure directly performance quality. So it's very hard to take a painting and say this says performance 3.2 or whatever that means, while it's very easy to count how many people go to the Louvre every day to see the Mona Lisa. So we use that as a proxy performance. However, there is a lot of evidence. There are also experiments in controlled conditions that show that performance and success, they are different. We work on assumptions that they are connected, but these connections is not well understood. and it's not trivial at all, and not necessarily to great performance corresponds great success, or behind great success there is great performance. So there are two different things. And back in 2013, I started thinking about studying better what success is, how we can model it, and how we can connect it to performance. So I want to go with you under the hood of what we were calling back then science of success. And then I will show a turning point in my career where I started thinking of success in a different way than in how the way I was thinking about it in 2013. And I will focus on success in science. Back in 2013, we were asking this question: how does success in scientific careers evolve? So we're not thinking about performance, we were just thinking of the evolution of success in a scientific career. We wanted to create models, predictive models of success. And we were narrowing down the question to two different questions. We wanted to know who is going to have an outstanding achievement and when in their career. And when I talk about careers, I have in mind something like this. I have in mind basically a time series that we can extract from publication data. So here we have the career of Richard Feynman, and each point in this time series is corresponds to a paper of Richard Feynman, and the position on the x-axis is the time of the publication of that paper, while the height of the dot corresponds to the success of that paper captured, or the impact of that paper captured by citations accumulated over 10 years. And what we wanted to do back then was to predict when a scientist, in this case Feynman, has their highest impact paper, and so we call it the star paper. When, so identify T star and predict the magnitude, so the impact of this highest impact paper. And I will not talk about this research a lot. I just want to summarize the two results that came out of this project, because they're important then for the discussion of biases. So we found that impact is random within a career. Basically, if we look at the T-star moment, so the moment a scientist in their career, in the moment the year when a scientist publishes their highest impact paper, this is basically undistinguishable from a null model where impact is randomly assigned to papers. So basically, if I take the career of Richard Feynman and I measure T star, and then I randomize that career by destroying the time order of the papers, so the highest impact paper can end up to be the first one, the second one, the third one, and I redo the same measurement, I basically find the same frequency of T star. This means that there is no magic aha moment in a career. Simply, scientists have very heterogeneous productivity, and if they are more productive, they tend to have their best paper in their high productive time. So impact is random within a career. This was one result of that research, and the other result was that there is an individual parameter called Q that can separate luck from skill and has predictive power, can predict career impact. So impact is random within a career, but there are differences in impact between careers that can summarize in a parameter, in a number, Q. And there is a paper, I'm not talking about all the predictions. If you're interested, you can easily find them online, all the results, and feel free to ask. But so when going back to our questions, we could answer these two questions. So who is going to have an outstanding achievement? These are likely scientists with high Q, with this high parameter that we identified, and when randomly within their career. And yes, so together with the paper, there is a video and also a visualization platform where you can look at the data and and see what are the highest Q scientists or the lowest Q scientists in different fields. But as I said a couple of slides ago, this was back in 2013. This was an important paper, an important research project during my postdoc. It also was published in a good venue that certainly helped me for all the following applications. But after that, after publishing this paper, funding officers started contacting us, the group, asking, okay, can you calculate the Q of this many scientists? Or how can we use Q to prioritize applications? Or is this Q better than the H index? And all these kind of questions that you can perhaps imagine or conceive yourself. And this is the moment, the turning point of my career. I really, started thinking, I said, what did I do, right? My objective back then was, yes, understanding how success evolves, creating models of careers, creating models of the evolution of success over time, but that never meant to create a better way to rank scientists. Or I never equated success and prediction of success with quality, right? I can see now in retrospective how things could go wrong when you think about success and performance and so on, but this was not meant back then. So, and then I said, okay, how can we undo things or at least correct for things, or in a more scientific way, how we can show that performance and success differ in science. And if we are interested in performance or in quality and not in success, how we can do that. And it all started from that project. And I started thinking, okay, how can we prove that performance and success are different? And the question was, for example, whether the parameter that we had identified, this Q, captures performance or not. One of the results of our research was that Q is constant within a career. So each scientist is identified with one value, Q. So it summarizes the output of a career. And then I said, okay, what we could do is measure Q in different segments of the population. For example, we can make a binary assumption, divide scientists in male scientists and female scientists based on their first name. It's we use, gender is not binary, we know, but we use this assumption, and we can measure Q, right? And what we found is that Q is systematically lower for females on average than for males. And so male scientists have on average a higher Q. And this can mean two things, right? Either if we believe that Q equates quality, right? Q corresponds to quality. Female scientists produce work that is on average of lower quality. I think that at this audience, none of us really buys this hypothesis, right? Or the other possibility is that Q is biased, right? Doesn't capture quality. but still captures success, right? And so that success is biased. And this is the usual problem, right? Quality cannot be measured in science. So how do we do? There are always these two hypotheses, right? That either there is a bias or this segment of the population, in this case, women produce work that is subpar compared to the one of men. These kind of questions can be answered causally only, or I think the best way to answer these questions is by doing controlled experiments. We can't do controlled experiments on citations. We don't have an environment where we can control for all factors and try to vary gender and see if number of citations changes. But we can take inspiration from works, randomized control experiments done, for example, in psychology, where they show that, so my favorite experiment is an experiment where they had to recruit research assistants, and committees of researchers were presented with identical CVs, where the researchers were changing only the applicant name. So the exact same CV was offered to different committees, and one committee could see the name Jennifer and the stated gender female, and another committee saw John male. All the other qualifications were identical. And the results of this experiment were shocking, right? So male students were considered more competent, more hireable, they were offered more mentoring opportunities, and they were offered a higher salary. And we can, if we go into the details of this experiment, there are some problems with effect size. The experiment can be, should be replicated with bigger sizes, but the idea is there. Performance of women tend to receive less recognition for the same performance. For their performance. So if a male does exactly the same things, is perceived as more competent, as more hireable, and so forth and so on. So what we wanted to do is replicate this, or try to do something as close as possible to a randomized controlled experiment, but with data. And we wanted to answer these two questions. How does productivity differ between female and male scientists? And how does impact differ between female and male scientists? Taming all the confounding factors that we could think of. So what we did was taking the careers as we saw before, associating each career with a gender based on the first name of the scientist. So on the publication, so we can see the first name, and we can use a name recognition software that gives the gender with a certain likelihood, and we work with a binary assumption. So each career becomes a female career or a male career. And we can study the different characteristics of the scientific careers over time, different parts of the world. So we measured everything that we could measure in these careers, like we could measure the differences in productivity, differences in impact, different indicators, and unsurprisingly, we found differences between the genders for everything that we measured. Let me summarize the most important differences that we found by measuring straight away without controlling for any variables. Men represent 70% of the scientific workforce in science. They have 30% more citations. They are more productive than women. Productive here means number of papers. And actually this productivity gap is increasing over time. So in the 50s, men were 10% more productive. In 2000, they were 35% more productive than women. However, if we look at the annual productivity, so how many papers on average per year a woman and a man produces, there is no difference between the two genders. So the annual productivity is the same. And the fact that men are more productive, but female and women and men have the same annual productivity can be explained by the fact that women have shorter career lengths. So if a woman tends to stay for a shorter time in academia, has less time to publish papers. And so we started looking into then the dropout rate of women. We know that women tend to drop out of academia at a higher rate than men. But what is interesting is that this dropout rate is not constant throughout a career. There are not distinguishable differences in dropout rate for the first 3 years of an academic career. So basically, based on this data, PhD students of both gender drop out of academia at the same rate. The gap starts around year 3 or 4, and it becomes the largest gap between the two genders occurs at year 6. So 6 years after the first publication. And then it continues all of the time. So women tend to drop at a higher rate, even 30 years, 35 years after a career start, which is depressing news. So it's not because a woman gets tenured, then that has less risks of dropping out. Academia still, even tenured professors tend to exit the system at a higher rate than men. So I was saying that we find differences in everything that we can measure, but we don't know what causes what. So there are a lot of confounding factors. The dropout rate is one of them. So to tame the confounding factors and create the closest thing that we can do to make an analysis which is as close as possible to a randomized control experiment, we can create matched samples and do a matched sample analysis. Basically, we, for each scientist that is female, so for each woman that is an American physicist with a given career length that works at an institution of a given rank, we find an identical male scientist that is male, but has all the other characteristics identical to the one of the woman. So we create two samples where all the variables match, at least in terms of distribution, and the difference is only gender. And the other difference is what we don't match. In this case, we don't match productivity and citations. So if we study productivity in the entire population, we saw that the men tend to be more productive, and that the productivity gap is 27% for the whole population. If we control for all the variables that I mentioned, including dropout and career length, this gap, the gap in productivity shrinks to 9%. If we look at the difference in impact in the population, the difference is 30%. If we control for all the variables, this the gap reduces to 12%. If we control also for productivity, so if we control for all the variables, discipline, country, institute, rank, and number of papers that men and women produce, and we look at the difference in citations, basically we find no differences at all between the two groups. So this was an effort to put causal links between the different variables, where we see differences between genders. So how does productivity differ between female and male scientists? Well, this differs only by now 9% if we take into account dropout rate, or if we take into account leaves, if you want. So a woman tends to be less productive, not because is less productive in shorter time periods, but because has less opportunities over a career to publish papers. And how does impact differ between female and male scientists? Well, basically there is no difference if we take into account confounding factors. So if we take into account the institution where a woman works or the number of papers produced, then papers have the same impact, basically. Okay, I'm going to wrap up. So there are many biases, and there is not just gender bias. There are a lot of ways where success does not coincide with performance. For example, there is a reputation bias, or there are biases in the way we manage to publish, for example, in important venues. This is something we have studied in the past. Or there is an interdisciplinary bias. We know that interdisciplinary research is hard, and it's hard to publish. It's hard to get funded for interdisciplinary work. So this also affects performance and impact. And in general, I think we have enough evidence that says that performance, success, and size differ. They do. We still don't know how they differ. So we have this disconnection between performance and success, not just in art, but also in science. And I think it's very important that we don't forget that success is performance. For example, when we sit in hiring committee, or when we have to evaluate the work of scientists in general, even when we open Google Scholar and we want to have an opinion about the scientists and look at those numbers on the right, say, oh, 3,000 citations, this person has more citations, that's the other one. They don't mean anything, because we really don't know how things can go wrong in this going from performance and success. As I said, we have an obsession about measuring things, and for a reason. We need to quantification, we need algorithms, we need to use data for many things. But then I think personally, but also as a community, we need to do more research in understanding how the data that we produce correspond to what we do. So what happens in this path from performance to success, if we want to use data about success for anything, for any application. And this is part of my research agenda, but also I think from a moral point of view, we need to do this. And thank you. I've been talking a lot. Just wanted to say that there is a village, so I have wonderful collaborators that work on this whole line of research. I don't have a list of them on screen, but this is definitely not solo work, but teamwork. Thank you.
Thank you so much, Roberta. This was quite a tour. I didn't expect all the twists and turns that we had along the way. I am going to say goodbye to everyone on YouTube.